Hello, this is Professor Bennett from digitalaudiotheory.com. This programming example, 10.2.1, covers a first-order IIR filter. An IIR filter, or infinite impulse response filter, has feedback terms in which the output is summed together along with the inputs and previous versions of the input. So consider the following simple IIR filter given by this block diagram. In order to write the difference equation, seen up there, the first step is to count the number of terms contributing to the output accumulator. We can see 3. We have 2 feed-forward and 1 feedback taps. The no delay tap has a gain of A0, while the unit delay tap has a gain of A1, and the unit feedback tap has a gain of B1. So the difference equation is given as the sum of these 3 terms. X of n times A0 plus X of n minus 1 times A1 minus Y of n minus 1 times B1. Now, for the transfer function, the feed-forward terms are collected in the numerator, and the feedback term ends up in the denominator. The transfer function for this filter is A0 times Z plus A1 over Z plus B1. To find the magnitude response, we'll start with the transfer function and evaluate on the unit circle by replacing Z, which can be representative of anywhere on the complex plane, with e to the j2 pi f over fs. E to the j2 pi gives us a circle. F over fs gives us a fraction, or some place along that circle. And as we vary f, which is the only variable, let me pull it up here. If we vary f, which is the only variable here, we can compute the frequency response at that frequency location. So once we've determined the frequency response, we can find the magnitude response. But we need to fill in our coefficients here, so we'll just select A0 to be 0.9, A1 to also be 0.9, we'll set B1 to 0.1, and we'll select a sample rate of 48K. So we'll define an array of frequencies to analyze, then convert to a digital omega. So here are our coefficients and sample rate. Here is our frequency array that we'll then convert to an omega array. So frequency, we're analyzing from DC in steps of 1 Hertz up to Nyquist, and omega is going to simply be, our digital omega is going to be simply our f over fs times 2 pi. So where we had a1 times z plus a1 in the numerator of the transfer function, we now have a0 times e to the j omega plus a1 in the numerator, and with a similar substitution in the denominator. And if we plot the absolute value of this, we can see the magnitude response of the filter. Numerator, denominator, put it all together to get the frequency response. If we plot the absolute value, we get the magnitude response. But we'll plot the dB of the magnitude. And we'll label our axes. There we have it, the magnitude response of this IIR filter. Now, without solving for the frequency response, we could use the freq command to plot the magnitude simply by passing the numerator and denominator coefficients. This function returns the complex frequency response in H1 and its corresponding frequency array in F. And what we'll see is that the magnitude plot matches the figure we generated. So here are the numerator coefficients are A0, A1, denominator coefficients are 1 and B1. We pass numerator and denominator to freq z. We pass the sample rate and the number of frequency points we want to analyze. Okay, so we're going to create a new subplot and show H1, so this is the one that's generated by MATLAB. And let's go ahead and show the phase as well. There's our phase. Now the phase is going to be given by, instead of the absolute value or the magnitude of H1, instead the angle. So last we'll plot the group delay of this filter using the GRP delay function. It also takes numerator and denominator coefficients, as well as the sample rate. So that's going to be saved into an array called GRD, and we'll set up a plot for that as well. Now, interestingly, you can see that this filter exhibits fractional delay. So our horizontal axis here are in samples. So the delay varies between 0.4 and 0.6 samples. So here we see a group delay is actually less than one sample. In a later programming example, a second order filter will be developed in which we'll be able to examine poles at frequencies other than 0 Hertz or Nyquist. But until then, thanks for watching.